So I'm going to start with a graph. So come over here. Back to our basics. If we're at 4, 2, there's point R. If I'm at -2, 5, there's point S. So my vector goes from R to S. Right? The order is important because your initial point, your terminal point, the vectors have direction. So it's not just like when you have line segments. In geometry, when you had line segments, it didn't matter if you said RS or SR. Vectors, it matters. So if we want to put this vector in component form, we are going to find the horizontal distance and then the vertical distance. So in component form, that's going to be x2 minus x1 and then y2 minus y1. Which when you look at that, you might say, Ms. Collier, isn't that kind of like the slope formula? Yes, slope is your change in y over your change in x. It's that ratio. And so that's what we have here. And so if I'm at if I'm at point R and I go horizontally, so that's the horizontal component of the vector. And then from that endpoint, I go vertically. So that's the vertical component of the vector. So I can see graphically that I went 1, 2, 3, 4, 5, 6, -6, and 1, 2, 3, +3. Algebraically, I plug in these values, -2, -4, and then 5, -2, and I have -6 and 3. So one of the things as we're learning vectors is I want the algebraic part to make sense to you and connect with the geometric part, right? It should all like go together in your head. It shouldn't be like this is over here in your brain and then this is over here in your brain. We want them to connect with each other. All right, so that's the component form of vectors. So another form that you will be asked to write in is linear combination. And so when we do linear combination, we are using unit vectors. So unit vector I is 1, 0. Unit vector J is 0, 1. And so basically I want to create this component vector by somehow combining these two unit vectors. So if I multiply -6 times I, that would equal -6 times the vector 1, 0, which would equal the vector -6, 0. Right? And then if I take 3 and multiply it by j, it's going to give me 3 times 0, 1, which is going to give me the vector 0, 3. And then if I combine these two vectors, if I add them together, that would give me -6, 3, because I add my horizontal components and I add my vertical components. So -6, 3 comes from doing -6I plus 3j. So your horizontal component is multiplied by your unit vector, I, and your vertical component there is multiplied by your unit vector, j. So these two vectors, it's the same vector, it's just two different ways to write it. Linear combination way, component way. All right, other thing we have been over already and practiced quite a bit, but it's on Look It, so I want you to get your questions right, is finding the magnitude. So the magnitude is the length of this vector. So you could think that's the distance from R to S, so it could use the distance formula. Or you might say, look, Ms. Collier, that's a right angle, and that's our C, so couldn't we use the Pythagorean theorem? Yes, and yes. So if I'm in point form, and I have x2 minus x1 squared plus y2 minus y1 squared, that's my distance formula. If I think about the Pythagorean theorem, C is the square root of a squared plus b squared. These are the same equation, right? Because when I come here, here's my difference of x's, that's A on my right triangle. Here's my difference of y's, that's B on my right triangle. It's the same thing. So if you're in component form, here's A and B. But if you're in point form, you'd subtract your x's, subtract your y's. So for the vector we have, it would be negative 6 squared plus 3 squared, which would give us the square root of 36 plus 9, which would give us the square root of 45, which would be the square root of 9 times 5. Square root of 9 is a perfect square, so 3 square roots of 5. Now, when we're playing Look It today, you're actually just going to take the square root of 45 and change it into its decimal equivalent. Your answers are going to be in decimals. All right, so initial point, terminal point, component form, linear combination form, and finding the magnitude. Those are the basics. Now, the other thing we're going to look at is vector operations. Pretty basic as long as you just know what to do. So if I have vector A in component form, let's say it's 4, 5, and I have vector B in component form, negative 3, 7. I can add vectors together, I can subtract vectors, I can multiply a vector times a scalar. I can multiply a vector and then add it with another vector. Okay, so when we say vector operations, those are all the things we're doing. So what if I wanted to do 3 times vector A plus vector B? So that would mean 3 times the vector 4, 5 plus the vector negative 3, 7. So when you multiply a scalar times a vector, this is very much like the distributive property. You multiply your scalar by each component. So 3 times 4 is 12, and 3 times 5 is 15. And then when you do addition with vectors, you add your horizontal with your horizontal, so you get 9. And then you add your vertical with your vertical, and you get 22. So that's operations with vectors. You can multiply, you can add, you could also subtract. All right, then the last thing before we play Book It is the dot product. So the dot product of two vectors, so if I have vector A dot vector B, that's A1 times B1 plus A2 times B2. So it's multiply the horizontal components together, multiply the vertical components together, and then add them. So for this example here, we would have 4 times negative 3 plus 5 times 7. So we'd have negative 12 added with 35, which would give us 23. So it's a very interesting thing that happens. You take a vector and you do the dot product with another vector, and you come out just with a numeral answer, 23.